In this presentation, I'm going to talk about minimum cost network flow problems. In your Winston's textbook, the materials in this presentation corresponds to the section 8.5. So minimum cost network flow problems is a generalization of the other problems that we have seen before. So you have seen the transportation, assignment, and transshipment problems before the midterm exam. And then in the previous videos, we've also seen the shortest path and maximum flow problem. And they all can be generalized, can be modeled as a minimum cost network flow problems. It's very interesting, right? A lot of other specific problems can be modeled by this minimum cost network flow problems. So let's see how we can model all those specific problems into this more general problem. Let's start with the formulation. So the objective function for this minimum cost network flow problems is quite simple. We would like to minimize the total cost of all flows that are going through our network, which means that we are going to multiply the number of units that is going through arc ij times the cost of transporting each unit of flow through arc ij. And then we take the sum over all arcs ij that we have in the network. So that's the objective function. Now we have two constraints here. The first constraint is called the flow balance constraint. Here, for each node in the network, we must make sure that all flows that is going out from that node minus all flows that is going in through the node must equal to the net supply of that node. So BI shows the capability of a node to provide a net supply. So how much it can supply. It can be positive. It means that it has the capability to supply more than it consumes. It can be zero, which means it can supply as much as it consumes or it receives. It can be minus if what the node receives is bigger than what the node can send through the other nodes. If we look at an illustration, so suppose we're in node I, and then this equation says that we need to take the sum of all flow that is going out from I, so I's supply, minus whatever is going in through I. So whatever is going in. So the first one is the outflow, the second one is the inflow. If we take the subtraction, so the outflow minus the inflow, we will get the net supply of node I. So that is the first constraint. The second constraint says that for each arc in the network, there is kind of lower bound and upper bound about how much flow you can pass through that arc. So Xij must be less than or equal to Uij, but it must be greater than or equal to Lij. Okay, so now we're going to model a transportation problem. It's a balanced transportation problem. So if it's not balanced yet, you have to make it balanced, right? Okay, so this is a balanced transportation problem. We're going to model it as a minimum cost network flow problem. So this is a typical table that you see in the transportation problem. You have the nodes, which are the suppliers. They have the supply capacity. You have also the demand nodes. They have the demand for each node. And then these values inside the small boxes, they are the cost from transporting from one supplier to one demand point. Now, we can also represent that table into a network. So each node is either a supply point or a demand point. We have two supply points and two demand points. And then the arc shows the possibility of transporting some units of flow from one supply point to one demand point. So one can supply point 1 can supply node 3, supply point 1 can also supply node 4. And then of course there's no arc going out from the demand point, because in the transportation problem, the demand points, they just need some of the units to be sent into them, but they are not sending out anything. Now let's model it into a minimum cost network flow problem. So first of all, the objective is we're going to say that we want to minimize the total cost of sending the goods from supply units to demand points. So here for each unit that we send from 1 to 3, the cost is 1. So 1 times x13. From 1 to 4, the cost is 2. So here 2 times x14. And then 3 times x23. And then 4 times x24. Okay, so what does x24 means? It means that the number of units that are sent from supplier 2 to node 4. Now it's the time to formulate the flow balance constraint for each node in the network. So we have 4 nodes here, and we're going to formulate the constraint for each of those nodes. So first for node 1, let's see what is going out from node 1. So we have x13 going out from 1, and then we have also x14 that is going out from 1. And then we see that supply point 1 has nothing going into it. So for all the other variables, it's just 0, and then it must equal 4. Why 4? Well, because if you see here, node 1 has the capacity of supplying 4. So the net supply of node 1 is 4. It can supply 4 and then it receives nothing. So the net supply is 4. Okay, and then in terms of outflow and inflow, we see that the outflow from node 1 is 4 because it is supplying 4 units to either node 3 or node 4, and that it has no inflow such that the net supply is 4. Outflow 4 minus inflow 0 equals 4. Now for node 2, we see that node 2 is also a supply unit, and then from node 2 things go out 2 to 3 and 2 to 4. So here 2 to 3 equals 1, 2 to 4 equals 1, and then 0 for the other. And then we see that the net supply of node 2 is 5. So for node 2, this right-hand side equals 5. And by the way, this numbers 1, 0, 1, 0 means that you need to multiply it with the x. So the complete equation says that 1 times x23 plus 1 times x24 equals 5. Okay, so that's how you read this table. And then for node 3, we see that node 3 has nothing going out of it. It has things going in from 1. It has things going in from node 2. So because things are going in to this node, we put minus on the corresponding variable. Let me repeat. Because node 3 only receives flow from the other nodes, so we put minus in front of the number ones here. So minus 1 times x13 because it receives from node 1, minus 1 times x to 3 because it receives from node 2, and then the net supply is minus 6. Why? Because the outflow from node 3 is 0, it sends out nothing, but it receives an inflow of 6. So the 6 is coming from here. So node 3 needs to receive 6 units of flow, but then it sends out nothing, so the net supply is minus 6. And then for node 4, I think I noticed a mistake in your book. So this thing here, it shouldn't be 1, because if you look at the index, it is x13. It has nothing to do with node 4, so it should be 0. Okay, and then same thing, you check out which flows are going into node 4. So from 1 to 4, from 2 to 4. So you have the minus if it is about going into the node because of this minus here. And then the net supply is minus 3 because node 4 sending out nothing, so outflow is 0, but it received 3 units. So outflow 0, inflow 3, so the net supply is minus 3. And then you need to say that all variables, all the flows in each arc needs to be non-negative. You may ask, do you need to specify the flow needs to be greater than or equal to the lower bound? Yes, this is for the lower bound, but what about the upper bound? Well, in this case, it's not necessary because all this flow balance constraint already says that the flow, let's say from 1 to 3, must not exceed 4, or the capability of node 1 to supply something. So you may, if you want to, you may say that x13 less than or equal to 4, x14 less than or equal to 4, that is okay. But really, this constraint already takes care of that upper bound constraint. Now, maximum flow problem can also be formulated as a minimum cost network flow problem. So these are the constraints of the flow balance constraint and the objective function. Remember that the objective of maximum flow problem is we try to flow as many units of things as possible from the source to the sink. And then we put an artificial arc saying that we want to maximize whatever is flowing out from the sink. So we want to maximize the flow out of the sink, which means that we should minimize minus of that flow. So I noticed again, I think another mistake in your textbook, 4th edition, it should be minimized minus x0, because x0 is the flow going through this artificial arc. We want to maximize that. So when we change to minimization, it becomes minimize minus x0. Okay, now let's look at the flow balance constraint. For the node source, we see that it goes out from source to 1 and source to 2. So source to 1 is 1, source to 2 is also 1, and then it receives something from the sink. So the flow from the sink to the source is denoted by x0, and then as usual, if it is an inflow, then the sign is negative. So do the same thing for the other nodes. Let's say, for example, node 2. So node 2 sends out from 2 to sink, so this is plus 1. But then it receives from 1 to 2. It also receives from source to 2. So these two, the values are minus 1. So let's take another example, the node sink. The only outflow is x0. x0 is this, going through the artificial arc. And then it receives an inflow from 3 to sink, and then from 2 to sink. So that's how you formulate the flow balance constraints. Now let's talk about the net supply of each node. Here you can see the right-hand side for each node equals 0 for all nodes. Why is it different with the transportation problem? Well, if you recall what we have seen in the maximum flow problem, all nodes in the maximum flow problem needs to follow the conservation of flow constraint. It means that whatever going into the node must be flown out of the node with the same amount, because we need to keep the flow that is going from source to sink, and then we also make the artificial flow that goes from sink to the source such that everything has that kind of balance. Whatever is going in must go out of that node in the same amount. So that's why here we see that the net supply for each node, even for the sink, equals 0. Now we need to specify the upper bound for each node. Sorry, for each arc, I mean. So let's say from source to 1, the upper bound is 2. Because you need to, you can only transport or pass through 2 units of flow from source to 1. Let's take another example. For example, from 3 to sink. You see here from 3 to sink, it cannot exceed this capacity of the arc, which is 1. So whatever is flowing from 3 to sink cannot exceed 1. And then you put 1 here because it is corresponding to the flow from 3 to sink. So these are the upper bound for every arc in the node. And then we also say that all variables must be non-negative. 0 is okay, but negative is not allowed. Now let's take a look at an example of a minimum cost network flow problems. You can see that this has some similar characteristics to the shortest path problem. It has also some similarities with the maximum flow. But you see that this problem is different with both because this is kind of more general. Okay, so we have an average of 900 cars enter the network at node 1, and they're all trying to reach node 6. The time it takes for a car to traverse each arc is shown on this table. And then you also see that there are numbers above each arc. So for example here, 100 here means that the maximum number of cars that can pass by arc 2 to 3 during this period is 100 cars. So it's kind of a narrow road, you may think of it. On the other hand, from 2 to 4, the road is wider. So in one period of time, 600 of cars may pass through the arc of 2 to 4. And then for this minutes, it takes 30 minutes for a car to pass this arc 2 to 4. And then it takes 70 minutes to pass this arc 2 to 5. So the numbers above the arc shows the capacity of this arc, and then the numbers on this table shows the time to pass through an arc. And then the objective of the problem is that we want to minimize the total time required for all cars to travel from node 1 to node 6. Okay, so the objective is to minimize the total travel time for all cars. Because it is related to time, so we are looking at this table. From node 1 to 2, it takes 10 minutes for one car. 10 minutes from one car. So we multiply that time for one car times how many cars passing through the arc from 1 to 2 in a period of time. Okay, do the same thing. Let's say for 4 to 6, it takes 60 minutes. So 60 minutes for one car. So because we want to minimize the total time for all cars, So we multiply this 60 minutes for one car times how many cars are traveling from node 4 to node 6. So the objective function is the sum for all these numbers. And then the definition of the decision variable is xij is the number of cars per hour that traverse the arc from node I to node j. So the unit for xij is cars, how many cars. And then these numbers corresponds to the time of traveling from one node to the other node. Now for the constraints, we have two types of constraint. The first one is the flow balance constraint, and then the second one, which we will see later, is about the capacity of each arc. Okay, now let's do the flow balance constraint for each node in the network. So for node 1, we see that nothing going in to node 1, so no inflow, but the outflow is x12 and then x13. So x12 equals 1, x13 equals 1, and then all the others equals 0. And then the net supply for this network is 900. Why? Because from node 1, 900 cars are flowing out from that node, and nothing flowing in to node 1. Now let's take a look at node 2. The outgoing flow from node 2 is x24 and x25. So the coefficients for x24 and x25 equals 1. And then the inflow to node 2 is from 1 to 2. So the inflow has a negative coefficient, so it's -1 for x12 in this constraint. The net supply for node 2 is 0. Why? Because remember, all the cars needs to be at node 6 in the end. So they are just passing through node 2. All cars that going into node 2 will goes out because their final destination is node 6. So it's the same case for node 2 up to node 5. Their net supplies equals 0 because cars are just passing through these nodes. And then finally in node 6, because this is the final destination, so it has the net supply of -900. Why? Because there's no outflow of node 6, so outflow equals 0, and there's inflow of 900 cars. 0 minus 900 equals -900. And then from node 6, there's no outflow from there, but it receives inflow from 4 to 6 and inflow from 5 to 6. Inflow is denoted by -1 in the coefficient. Now, what about the capacity? So we see, for example, arc12, it can hold at most 800 cars an hour. So x12, the coefficient is 1, less than or equal to 800. Again, when you read this row, you read it as 1 times x12 less than or equal to 800. Let's see another example. Let's say from 5 to 6. You're saying here that 1 times x56 must be less than or equal to 600. Finally, for the lower bound constraint, you say that all variables must be non-negative, which means that for each arc in the network, you cannot have a number of negative cars that is going through that piece of arc in the network. So this is the formulation of the minimum cost network flow problem for that example. We have formulated the objective function, decision variable, constraints, and the lower bound and upper bound for each decision variable. Before talking about how to solve a minimum cost network flow problems, I'm going to talk about minimum spanning tree problem in the next section. The reason I'm not solving that problem yet, because we need the concept of spanning tree, which will be explained in the next section, to solve that minimum cost network flow problems. So see you in the next section. Thank you.